Okay, we're going to continue now with Chapter 13. The next thing that we're going to consider is the concept of transmutation and half-life. Now, in the previous video, we talked about how in certain types of nuclear interactions leading to radioactivity, that the nucleus of a particular atom can transform itself somehow. It can emit neutrons or protons or have neutrons change into protons. All of these things represent a kind of transformation or transmutation from one material into another material, from one isotope into another isotope, or even from one element into a different element. And this process where there's a transformation and something is ejected out of the nucleus of an atom, that's called a decay, a radioactive decay. And we can talk about the rate at which the decay of an element happens. How quickly does this transformation undergo? And the way that we usually characterize this is we talk about the half-life of the material, the half-life. And so the half-life is the rate of decay for a radioactive isotope. And specifically, it's the time that is required for half of an original quantity of an element to decay. So let's say I have a block of radioactive material and it's undergoing radioactive decay. It's sending out radiation, and as it's doing that, parts of its inside are transforming from one material into another material. Well, eventually, over time, about half of that material will transform from the original material into the new material. And the time it takes for half of that material to transform, that's called the half-life. And I want to be clear in my drawing here, my very crude drawing, I'm not trying to say that just the left half transforms. It's really chunks scattered out, but I've cut it in half to kind of indicate that over a certain length of time, if this radioactive process is ongoing, half of that material is going to transform itself into a different material. And just as an FYI, it's important to know that the half-life of material is constant and it's independent of any physical or chemical change the atom may undergo. That's because this is tied actually to the nucleus of the atom itself, not its chemical properties. And another thing is that it can be calculated at any given moment by measuring the rate of decay of a known quantity using a radiation detector. In other words, I take a certain material and I measure how long it takes for half of that material to decay, then I can measure the half-life. So let's look at one of these little check our understanding quizzes. We have a certain isotope has a half-life of 1 day. So it takes 1 day for half of the material to decay. What will be the amount of the original material remaining at the end of 2 days? Your possible options are 0, 1/8, 1/4, or 1/2. So let's just think about it. I start out with a block of pure material, and after 1 day, that's 1 half-life, half of the material has decayed into something else. So this down below is representing the parts of the material that have decayed, and the parts above are representing the amount of the original material that's left after 1 day. Now what's going to happen after the second day? 1 more day represents 1 more half-life. So half of this material will also decay. And so after the second day, we can see that another half of what's remaining has decayed. And how much is left? This is the part that's left. And I hope you can see that this is a quarter, because you have, after the first day, you've got half of the material, and then the second day, you've got half again. That leaves you with a quarter, because a half times a half is equal to a quarter. So the answer is C. 1/4 is what's remaining. If you let it go another day, you'd actually end up with an eighth left, because half of a quarter is an eighth. Half of what's remaining, this quarter is what's remaining. On a third day, half of that would be what was left over, and half of a quarter is an eighth. So we can note here, we're still talking about half-life of a material and the material's transmutation from one material into another. Radioactive isotopes decay at a rate characteristic of each isotope, and the rates are described by the half-life. The shorter the half-life of a substance, the faster it disintegrates and the more active the substance. And so we can see here kind of a chart showing if I start with a kilogram of a pure substance, if the half-life is 1620 years, after 1620 years, you'll have only a half of a kilogram of the original substance remaining. You let it go another 1620 years, that gives you 3240 years, and then you'll only have a fourth of the original material remaining. And then you let it go another half-life, another 1620 years, from 3240 plus 1620, that gets us up to 4860. Then you'll only have an eighth of a kilogram left, an eighth of the original amount. And if I went another half-life, again, the amount of original material would be cut in half yet again. So each half-life represents the time it takes for half of the original material remaining to decay and transform into the other materials. Now, generally speaking, when you have this kind of transmutation, there's two different ways that elements can be transformed. One of them is through what's called natural transmutation. And this is the changing of one chemical element to another occurring in sort of natural events. It just sort of naturally and spontaneously happens. There's another way that we can create this kind of transmutation, and that's done artificially in lab, where we do something to the material to cause it to undergo one of these reactions, and that's called artificial transmutation. Here we see a process of natural transmutation. And if we look down at the picture, we can see that this is an element of uranium-238. It has an atomic number of 92, so that means it has 92 protons, and it has 238 nucleons. That's its atomic mass number. So if you subtract 238 from, if you subtract 92 from 238, you end up with 146 neutrons. So uranium-238 typically is going to have 92 protons and 146 neutrons. Now what happens is that this material, U-238, can spontaneously emit radioactively alpha particles. And so what happens is the alpha particle consists of 2 protons and 2 neutrons. So when it gets emitted, what's left over is 2 less protons and 2 less neutrons. So we go from 92 protons to 90 neutrons, and from 146 neutrons to 144 neutrons. Now where did they go? They got emitted out of the nucleus of the atom as an alpha particle. And so we see here we've got 2 protons and 2 neutrons. The 0 is for a neutral particle. And so that's indicating that this guy is shot out and this guy has transformed itself. Now we can actually write down a chemical equation for this. You can say that 238.92, that's the atomic mass and the atomic number, the uranium yields thorium plus the alpha particle. And so what's happened is that uranium has spontaneously transformed itself into thorium, and in the process emitted an alpha particle as its radioactive decay. And as we noted previously, you can see that when an atom emits an alpha particle, its atomic number decreases. So we've gone from 92 to 90, it decreases. Now we can look at some of the other kinds of radioactive decays that we've talked about. For a beta emission, that's where a proton turns itself into a neutron and then emits an electron as a beta particle. There's no change in the mass number, no loss in the number of nucleons, because that proton turned itself into a neutron. Well, neutrons and protons basically have the same mass, so you don't change the mass of the particle. But what you have done is you've increased the atomic number by 1, because now that atom has an additional proton compared to what it had before. And so that means that the resulting atom belongs to an element one place forward in the periodic table. It's gained 1 proton, so it goes up 1 space in the periodic table. It's been transformed. Now, if you have a gamma emission from a nucleus, there's no change in atomic mass number, and there's no change in atomic number. Now, here's an example of what we call an artificial transmutation. And this was one of the first examples of this that was discovered way back in 1919. A guy named Ernest Rutherford did an experiment where he took some nitrogen gas and he bombarded it with alpha particles. Basically, he had a radioactive material that emitted alpha particles, and he set it next to a container of nitrogen gas. And what he found is, as those alpha particles entered into the nitrogen gas, they interacted with the nitrogen and caused the nitrogen to undergo a process by which it radioactively decayed and transformed itself. And you can see this depicted here. So we've got nitrogen, which has an atomic number of 7 and an atomic mass of 14. And it was struck by this alpha particle, which is essentially, if you'll remember, a helium nucleus. And in that process, it gained a proton and it gained 2 neutrons, but one of the protons from that alpha particle did not get absorbed. And so it got shot out, but the other proton and the 2 neutrons did get absorbed, and that caused a transmutation. So the nitrogen turned into an isotope of oxygen, and then we had this spare proton floating about, and we know that's actually the nucleus of a hydrogen atom. And so if it's able to grab an electron out here somewhere from one of the other atoms in the atmosphere, it would become hydrogen, and this guy would be oxygen, and we would have transformed the nitrogen into hydrogen and oxygen. All right, let's look at this, check our understanding situation. So the question is, when an element ejects an alpha particle, what happens to its atomic number? And we know that an alpha particle is 2 protons and 2 neutrons. So if it ejects an alpha particle, it's lost 2 protons. That's what determines its atomic number. And so its atomic number will decrease by 2. And so the answer is A. It reduces by 2. And the next question that we want to look at, it's really the same question, but what happens instead of ejecting an alpha particle, what if it ejects a beta particle? So when an element ejects a beta particle, what happens to the atomic number of that element? Well, we know that a beta particle is an electron, so the nucleus has ejected an electron, and in order to keep the charge constant, a neutron is turned into a proton, and that means that the atomic number has increased by 1. So the answer should be B. It increases by 1. Now, this next topic is a really cool application of this principle of radioactive decay. If you have something that undergoes radioactive decay and has a half-life, you can use that to determine how old a sample is. And so, for example, if I've got some mummy that's in some tomb in Egypt and I want to know how old is that mummy, I can actually use this process of radioactive decay to date how old the remains of that mummy are. One of the most common ways that this is done is with what's called carbon-14 dating. And carbon-14 dating is used for dating plants and animals. And basically, plants breathe in carbon dioxide and release oxygen. And people, we eat plants or we eat animals that eat plants. And so we're taking in the same type of carbon that those plants are taking in. And basically, what you'll find is that each of us, because we're all alive and we're all eating and we're all breathing, our bodies have the same ratio of carbon-14, which is radioactive, to carbon-12, which is the normal stable form of carbon that's not radioactive. So a certain percentage of carbon is carbon-14, and some of it is carbon-12. And we're constantly taking this in because we're breathing and we're eating and we're taking it into our body. Now what happens is once you die, you're no longer eating. You're no longer breathing. And so you're no longer taking in fresh supplies of carbon-14. And so when you die, your body has the same ratio of carbon-14 to carbon-12 that a living person has, but as time goes on, your radioactive carbon-14 starts to decay. And so it gets less and less relative to the carbon-12. And so what scientists can do is they can take a tissue sample, say from a mummy, and they can measure what percentage of carbon-14 there is compared to carbon-12, and they understand the half-life of carbon-14 is about 5760 years, 5,760 years. We can measure that in a lab, and so we know that the half-life is this long. And so if you take the ratio of the two types of carbon in a living person, that's sort of your baseline. And when someone dies, the carbon-14 gets less and less and less through radioactive decay. So if you take, say, the sample from a mummy and you find that they have half the amount of carbon-14 that a living person would have, you know that that mummy has undergone one half-life, or that mummy is almost 6,000 years old. That would be a really old mummy, by the way. But I hope that that makes sense. That process of radioactive decay makes sense, and how we can use it to understand how old something is. Now, non-living things, things like rocks and meteorites that come from outer space, these are dated through uranium and lead isotopes. So let's say I have a block of pure uranium. Uranium consists of primarily of two different isotopes. We've got uranium-238 and uranium-235. Uranium-238 decays into lead-206, and uranium-235 decays into lead-207. And so if I have a sample that's got pure uranium, it's going to start decaying into the different forms of lead. And a part of it that's 238 will decay into one type of lead, and the part of it that's uranium-235 will decay into another isotope of lead. But basically, if I get a sample of uranium and I test it and I find that a certain percentage of that is lead, I can determine how much lead there is compared to how much uranium there is, and I can look at each type of lead and each type of uranium, and I can use that to figure out how old that rock is that contains that uranium and contains that lead. So let's look at an example. An archaeological dig uncovers an ancient wooden spear whose wooden handle contains 1/8 the radioactive carbon of a fresh piece of wood. The question is, how old is the spear? Well, first of all, let's remember that the half-life for carbon-14 is 5760 years. So how many half-lives are we talking about? So we start out with one half-life, and we have half the original material remaining. And then we have our second half-life, and we end up with a quarter of the original material remaining. And then we have our third half-life, and then we end up with 1/8 of the original material remaining. So that tells us that if we have 1/8 of the original radioactive carbon, that's the carbon-14, that carbon has undergone 3 half-lives. And so if I multiply 3 times 5760, that's going to be how many years old that spear is. And what we find out is that 3 times 5760 is about 17,280 years. So that would be how old that spear would be. And so this is one of the things that has enabled us to understand so much about our world and about the universe we live in. The ability to tell how old stuff is using this basic physical principle of radioactive decay and the half-life of material. And I want to underscore this very important point that when you talk about the half-life of something, that's a universal constant. It's true for every atom of that material in the universe. So that seems like a good stopping point for this part of the lecture. So we're going to take a little break, and we'll come back in the next video and finish out the chapter.